Hi everyone. Today we're going to study universal quantifier. There is another important way called quantification to create a proposition from a propositional function. Quantification expresses the extent to which a predicate is true over a range of elements. In English, the words all, some, many, none, and few are used in quantifications. The area of logic that deals with predicates and quantifiers is called the predicate calculus. Now let's study universal quantification. Many mathematical statements assert that a property is true for all values of a variable in a particular domain. Such a statement is expressed using universal quantification. Note that the domain specifies the possible values of the variable x. The meaning of the universal quantification of p of x changes when we change the domain. The domain must always be specified when a universal quantifier is used. Now we have universal quantifier. The universal quantification of p of x is the statement p of x for all values of x in the domain. The notation inverted A x p of x denotes the universal quantification of p of x. Here, this inverted A is called the universal quantifier. We read inverted A x p of x as for all x p of x, or for every x p of x. An element for which p of x is false is called a counterexample of for every x p of x. Note that if the domain is empty, then for every x p of x is true for any propositional function p of x, because there are no elements x in the domain for which p of x is false. Let's have example 1. Let p of x be the statement x plus 1 is greater than x. What is the truth value of the quantification for all x p of x? The domain here is the real numbers. Because p of x is true for all real numbers x, the quantification for all x p of x is true. Example 2. Let q of x be the statement x is less than 2. What is the truth value of the quantification for all x q of x? The domain is the real numbers. Q of x is not true for every real number x. Let's find a counterexample. Let's say x is 3. So we have this q of 3. Substituting the number 3 to that statement, it becomes 3 is less than 2, which is false. That is, when we set x equal to 3, that is a counterexample for that statement for all x q of x. Thus, for all x q of x is false. Example 3. What is the truth value of the universal quantification of p of x colon x squared is greater than 0? The domain here, all integers. To show that the statement for all x, p of x is false, where the domain consists of all integers, we give a counter example. We see that x equals 0 is a counter example because x squared equals 0 when x equals 0, so that x squared is not greater than 0 when x equals 0. Therefore, for all x, p of x is false. Example 4. What is the truth value of the universal quantification of p of x colon x squared is less than 10? The domain here is positive integers not exceeding 4. The statement for all x, p of x, is the same as the conjunction p of 1 and p of 2 and p of 3 and p of 4. Because the domain consists of the integers 1, 2, 3, and 4. Because p of 4, which is the statement 16 is less than 10, is false, it follows that for every x, p of x is false. In here, the number 4 is the counter example. I hope you learned something from this video. See you again next time.